Ground-based telescopes have a problem, and that problem is that they have to observe distant objects through our Earth's atmosphere. Okay, and we know that our Earth's atmosphere, we've got wind, we've got clouds, the layers of our Earth's atmosphere are constantly moving around. And so what happens is that light coming in from our distant star gets refracted or bent when it moves through our atmosphere. And that how much it gets refracted or bent is dependent on the conditions of the atmosphere at that time. Whenever you look at a distant star and you see it appear to twinkle, it's not the star that's like flashing off and on for you. What's happening is that the light coming from that star is being bent within the Earth's atmosphere that sort of shifts around our ability to see that star as being one pristine point source. And that's the twinkle, twinkle, little star. That's the twinkling of our stars. And the temperature and density differences in pockets of air through which that light from the distant star is moving impacts the image that we see of those stars in telescopes or with our eyes. Now, things like the moon or the planets, Jupiter, Saturn, Mars, when we can observe them with our naked eye, Venus, Mercury, those don't appear to really twinkle like the distant stars do. They don't appear to twinkle because the planets are a little bit closer to us, and they'll appear to be a little bit bigger in the sky compared to those distant stars. And so the light coming from them isn't going to be impacted as much by atmospheric distortion as it moves through the atmosphere to our eyes. We give the twinkling of stars in the sky a term called scintillation. Right here, it's spelled out for you. And again, it's caused by moving atmospheric irregularities refracting starlight. The condition of the sky for viewing is referred to as seeing, or the seeing conditions. So if you go to observe at a telescope and they tell you that the seeing conditions are not good, that means that there's a lot of atmospheric distortion occurring that will impact your ability to get really pristine images of whatever you're trying to observe in space. Now, this distorted seeing can be improved by something called adaptive optics. And I think some of you already learned about this whenever you were researching different types of telescopes for your discussion last week. Okay, so what happens in an adaptive optics system? I worked at a telescope one summer that had an adaptive optics system, and my job was to perform computer simulations to understand how the telescope would behave with the particular adaptive optics system that they had in place. Imagine that we have a very distant star. Here's my distant star in yellow. And we have light coming toward us from that distant star. Here's that light. See, I'm drawing it in our wave view of light here. I've got crests and troughs, and the wavelength is the distance between consecutive troughs here, or consecutive peaks. Now, this light is coming off from the surface of the star in all directions. All over the surface of the star, this light is emanating out. And what I'm going to do is every place I see a trough here, we imagine that there's a spherical shell, kind of like this, a spherical shell of light, okay, coming off of that star in all directions. And so I'm not doing a very good job of drawing these spherical shells here, okay? And so by the time that light reaches the Earth, okay, that spherical shell is no longer quite spherical. That what we call wavefront of light, which is essentially these black lines that I'm drawing here, that wavefront of light, by the time it reaches the Earth, is essentially sort of a flat plane like this, okay? When it reaches the Earth, here I am, this is our wavefront of light. Here I am observing that light coming in on the Earth. But what happens is that once that light wavefront enters our Earth's atmosphere, the Earth's atmosphere sort of distorts that wavefront of light, kind of like this, okay? If this was the wavefront in space, once that wavefront of light enters our Earth's atmosphere, it gets distorted. Okay, and then that is what causes the twinkling of the starlight that we can see. Okay, and what happens is that telescopes that have an adaptive optics system, they are able to detect how this light is distorted when it's moving through the Earth's atmosphere. And what those detectors do, those adaptive optics systems do, if this is our distorted wavefront, what those adaptive optics systems do, which we sometimes abbreviate as AO, they observe this deformation in the pattern of light coming in from the distant star, and they tell the telescope mirror to do the opposite. So on the back of a telescope mirror, there are these little motors that we call actuators that can actually deform or bend the surface of the mirror that we're using to reflect the light toward the primary focus of the mirror to observe these distant objects. So the adaptive optics system is smart. It's getting that information about how deformed this wavefront is of light coming in from that distant star. And then that AO system tells our telescope mirror to do the opposite. So let's say that this, then I'm going to try to mimic the opposite of what I just drew here. This is how my telescope mirror will be deformed. That adaptive optics system is smart. It can figure out how exactly this wavefront of light has been distorted. And then it tells these little motors on the back of a mirror that we call actuators to deform the mirror in different ways. Deform the mirror essentially to exactly undo the distortion of the wavefront that was caused by our Earth's atmosphere. For astronomers, we do not stand at telescopes and look at space objects through the eyepiece of a telescope. In fact, most of us don't even travel to telescopes. The telescopes can do these observations on their own with us being remote and never having to be there. A lot of these telescopes that are doing astronomical observations for us for research are robotic, or there are operators who are at the telescopes who are performing the observations for us. So we just tell them where to point the telescope and for how long and what instrument to use. So for many astronomers, operating a computer and being able to program are more important than being able to use a telescope. A lot of telescopes, again, are robotic. So these computers that are running these telescopes can accomplish several tasks. They can solve equations for us. They move telescopes around and change out detectors. They convert data into useful forms for us. And they provide a network of communication and data exchange. So we can collect data from a telescope without even having to be there by doing it from the comfort of our own living room in our pajamas. Telescopes can observe space objects in many, 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 many different wavelengths of light, not just the visible. So many astronomical objects radiate in colors or wavelengths of light other than the visible wavelengths of light. For example, cold gas clouds radiate in the radio wave end of our electromagnetic spectrum. Dust clouds radiate in the infrared part of our electromagnetic spectrum, and hot gases around black holes emit X-rays. And we've already talked about how the temperature at which an object is emitting light will determine the wavelength of light that's observed. We mentioned radio waves. Radio telescopes are examples of ground-based telescopes that observe in non-visible wavelengths. They're observing in the radio wave part of the electromagnetic spectrum, which is the part of the electromagnetic spectrum with the longest wavelengths of light. So these are radio telescopes. They don't have mirrors. They don't have lenses. They're satellite dishes. They're these giant dishes. They do focus the incoming radio wave to a point like our mirror telescopes are doing. Here's another radio telescope. This one is called Arecibo, and it's in Puerto Rico. If you've ever watched the movie Contact, this telescope plays an important role in that movie. We have this giant dish in the ground. Light is coming in radio waves, striking that dish, and it's being reflected up toward the focus of that dish, which is actually right here, which is where all the detection instrumentation is hanging. But Arecibo just recently had a problem, and part of the dish has fallen apart and collapsed. So currently, it's not operational. Arecibo plays a role in something called SETI, the search for extraterrestrial intelligence, where we're using these radio wave telescopes in order to see if you can capture perhaps a signal from a distant communicating civilization. Because of Earth's atmosphere, some wavelengths of light are blocked from reaching the ground. And so what I'm going to have you do for this engagement check is to think about where would you put a telescope to observe a particular wavelength of light. So here is a graphic that really shows us what's going on here. Here's the Earth's atmosphere. And then here on top, we have the portions of our electromagnetic spectrum. And what's happening here is that, for instance, in the visible part of the electromagnetic spectrum, that light is able to penetrate, those wavelengths of light are able to penetrate all the way through our Earth's atmosphere. And so we are able to observe on the ground invisible wavelengths of light. But you can also observe in space invisible wavelengths of light too. Over here in the radio waves are also able to penetrate through our Earth's atmosphere. You saw those radio telescopes needed to be super large to collect the radio waves, those giant satellite dishes. It makes more sense if radio waves are able to penetrate through the Earth's atmosphere that you build a radio telescope on the ground rather than wasting all that effort to put it into space. Now over here, and also radio waves, because they have such long wavelengths, are not really impacted that much by distortions in the Earth's atmosphere. Now over here, we have our shorter wavelengths of light. Those are things that are higher in energy. We have ultraviolet wavelengths of light that are actually absorbed by portions of our Earth's atmosphere. And so ultraviolet wavelengths of light don't always reach the ground, especially if we're talking in what we call extreme ultraviolet, which is closer toward the X-ray end of the electromagnetic spectrum. So X-rays do not really penetrate through our Earth's atmosphere either, and neither do gamma rays, those most highly energetic events going on in our universe. Here's another image that I'm going to have you analyze for the engagement check. We say that we are opaque to a particular wavelength of light whenever it is completely blocked by our Earth's atmosphere. So we see here that in the X-ray and most of the ultraviolet part of the electromagnetic spectrum, that ozone and oxygen in our atmosphere completely block the ability for those wavelengths of light to reach the ground. Here we have what's called the visible window, where in this wavelength of light, light from distant objects is able to penetrate through our atmosphere. This is a small infrared window through which we can observe on the ground a little bit of infrared wavelengths of light. Once we get to longer infrared wavelengths of light, water and carbon dioxide in our Earth's upper atmosphere block our ability to see these longer infrared wavelengths of light from the ground. So maybe you need to observe them higher up above the Earth's surface. Before we end, I want to talk about the future of large telescopes, both in space and on the ground. Hubble, launched in 1990, has been around for 30 years. Hubble is reaching the end of its life. It has done so much great science for us in 30 years. Hubble was launched by the space shuttle. The space shuttle missions have been discontinued. We used to be able to repair Hubble through space shuttle missions, but since there's no more of those, we're not repairing Hubble anymore. But the next big telescope to replace Hubble is called the James Webb Space Telescope. And this is what it looks like here. It's currently being worked on right now by NASA scientists. It was supposed to have launched a couple of years ago, and its launch window keeps on being delayed because they keep on finding things that they need to fix and be sure that are operating correctly on this very expensive, very important telescope before they commit to launching it. Here's what the James Webb Space Telescope looks like. It's going to be a giant mirror out in space. And you see that the mirror is actually broken up into these little hexagon shapes. And these hexagon shapes fit together to essentially create from smaller mirrors a larger mirror. So it's going to fold up kind of like origami. And then whenever it gets in orbit, it's going to kind of unfold. And these little foil pieces that you see here are shades that can come out to shield or protect the telescope from the sun, depending on its location around the Earth. And this telescope is called the 30-meter telescope. And as the name suggests, the diameter of this telescope is going to be 30 meters across. You can see it's made up of little segments, kind of like the James Webb Space Telescope is. This telescope is to be built, or it is currently being built, on a mountaintop in Hawaii called Mauna Kea, where there are a lot of other telescopes as well. But building telescopes like this is incredibly, well, it can be destructive to the land, and it's being built on, sacred native Hawaiian ground. So there's been a lot of controversy over this telescope, but they're finally going through with some plans to continue building this telescope. Before we end, I wanted to show you the comparison of sizes for some of these telescope mirrors so you can really get a sense of scale. Down here we have a basketball court. We've got a tennis court. Here you can see that the 30-meter telescope is about the same diameter as the length of a basketball court. In comparison, here we have the Keck telescopes that I was talking about earlier. We have down here the mirrors for the James Webb Space Telescope, and here is the mirror for Hubble. So you can see definitely how much bigger the light gathering area will be for the James Webb Space Telescope as compared to the Hubble.